Thank you for the nice introduction. So today I will talk about concentrated solar power, and I'll start with an introduction. I was told I need to give a background, so I'll start with an introduction, how electricity is made and what are the challenges. I will then just briefly describe several technologies for renewable energy, such as hybrid electric, wind, geothermal, and of course solar. I will say a few words about solar power and the main parameters that we need to use in order to design a system. And then I will talk about concentrated solar power. I will start with describing two major configurations, which is the trough configuration and tower configuration. And then I will describe what I was involved in, which is the concatenated micro tower, which is supposed to have better efficiency, and this is what I will describe. Then I will summarize. So, how electricity is produced? Actually, this is based on the idea that when magnets are moved near a wire, an electric current is generated in that wire. And this is based on the ideas of several ingenious researchers, such as James Maxwell, André Ampère, and Michael Faraday. And how it does work is that we have a magnet, and this magnet is, let's say at this point it is steady, and in the magnetic field of this magnet we rotate a wire, and this wire, while it is rotated, current is generated in this wire, and this is what we see here. This is the AC current that we use in our daily life. Another way to produce this is to move the magnet and to have the coil of wires steady, and this is what we do in the dynamo that is used in our bicycle. So there are other ways to produce electricity, for example in electrochemical cells where we use batteries or fuel cells, but we are not going to discuss on them today. So how do we do it in a large scale? How do we generate electricity in a large scale? So here we can see a coal fire power plant where we have the coal supplies running through a giant boiler where it's heated to high temperatures. And this high temperature are used to generate steam, which runs in these pipes. And this steam eventually goes with high pressure and high temperature. It goes to the turbine, where it is running this rotating wire that we talked about earlier, and this is what generates electricity. So, and later on, after the steam is cooled down, it's run back through the system to be heat again. And here you can see the motor. This is the steam entry, this is the rotor, and this is the magnetic field that I talked about earlier that generate electricity. And this is the actual size that you can see of the rotor, which generates enough electricity for the entire plant. So this coal factory is very hard to replace, because coal is abandoned, it's very cheap, and it is you can place it anywhere. You can place this plant anywhere and to have power supplied to you. So there is a high barrier here to overcome if we want to replace it. And why do we want to replace it? Because most turbines today are fueled with natural resources such as coal, petroleum, oil, and natural gas. And this cannot be replaced as fast as it's being consumed. Therefore, in the future, their availability is going to drop and their cost is going to increase. Also, the flue gases cause air pollution, and of course global warming due to the greenhouse effect. So let's describe a little bit about renewable energy sources. So at first there are the electromechanical power plants which generate electricity through the rotation again of the rotor, but due to mechanical change. For example, here you can see hydroelectric plant. Hydroelectric is the most oldest renewable energy source that was used, and it was used in dam using the water reservoir to have high pressure fluid coming through and rotating this rotor, which again generate the electricity. And there are small hydro plants, micro hydro plants, which just use the stream of the water, the river's stream, to rotate the rotor and to generate electricity for the small or rural places and few houses, not just as a major power plant. Hydroelectric plants are very common. Actually, it's about, as you will see soon, this is one of the most used renewable energy sources. However, it cannot be placed everywhere. Of course, you need to have a water reservoir, and it's not always available. And also, there is some problem with the environment. When you change the environment, if you put it down, you change the environment and you cause some damage to the environment. The other source of electromechanical power plant is wind turbines. Wind turbines can be placed at the offshore or onshore, and they can be used to generate electricity. Actually, this is very cheap way of using of renewable energy. And however, this again uses direct generation of electricity via the wind. So if you don't have wind, you don't have electricity. And this is one of the problems of wind turbines today. Another source of direct generation of electricity is photovoltaic. Photoelectric, you have the photovoltaic panel, as you can see here. When you generate electrons via the solar radiation, generating directly from photons to electrons. And this photovoltaic is actually one of the rapid growing market today in the world for renewable energies, and they are used to generate electricity. However, as it is in wind turbine, if you don't have sun on that day, so you don't have power generation. The last way is the steam power plants. The steam power plants are based on steam, generating steam, as I said before. However, the way to generate steams can vary. For example, geothermal, where you use the heat from the ground, deep down in the ground, you use the heat, you use a heat exchanger to to deposit heat and transfer the fluid, or the water, or the air into steam or superheated steam. And this steam is, again, what drives the turbine to generate, to move the rotor here and to generate electricity. Geothermal, again, it's very clean. However, it's not available everywhere. It's very useful for rural places, though. Another way to generate steam is to use concentrated solar power, which I'm going to explain soon. I didn't mention here, which is not considered a renewable energy source, the nuclear plants, but this is also, nuclear plants are also based on steam power plants, and you use the nuclear power to heat the fluid or the air in order to generate steam, and this was run the generator. This is the market share today, for the world market share today, for different sources. For example, fossil fuels is around 80% of the use of what generates energy today. The second most common is the traditional biomass, usually for heat or just to cook. And this small portion is the nuclear power plants. And among these 19% of renewables, you have, as I said before, the hydropower is very common, very used. Biofuels, and here now a small percentage are the wind, solar, geothermal, and biomass. Okay, so here we come to what our purpose is. Our purpose is to capture the sun and to harvest its energy towards making power generation more cheap and available. And here I want to describe to you three main methods to use the solar power and to generate energy. The first one is solar thermal collector, where we use solar thermal to heat either water, usually water, and to use it to house heat or to make hot water or for industrial processes. The other method to use solar energy is solar thermal collectors, where you collect the solar energy, you transfer the heat to a power plant where you have a power cycle such an engine or turbine, as I described earlier, and this is used to generate electricity. The third method is the photovoltaic collectors, where you generate electricity directly from the photon. As the photon hit the cell, electricity is generated. All three methods can be used with storage ability. For example, in solar thermal, as you will see, this is most effective one. Also in photovoltaic, you also have voltage, but not as efficient and not in large scale as it is in solar thermal. Okay, so let's learn a little bit about solar power and about the sun, which is used to generate this power. The intensity of radiation leaving the sun is relatively constant, and when it arrives just outside of the Earth, this point is just outside of the atmosphere of the Earth, you get about 1367 watt per meter square. This constant, this is referred to as the solar constant, and this value doesn't change much throughout the year. This depends on the distance between the sun and the Earth. It does depend because the Earth has an elliptical orbit around the Earth. So during different days around the year, you can have different distance towards the sun. So this distance change for about 3 to 4%, and therefore this constant change throughout the year. So you have at different times of the year different radiation. Actually, in the winter, you are closest to the sun, and you have so this factor, this constant is higher at this point of the year. Another factor that we need to remember when we deal with solar energy is its spectrum. Here you can see the solar spectrum just outside the Earth. This spectrum is mostly at the visible range, which is between 300 or 400 nanometer to 700 nanometer. In this range, this is most of the energy. Here, this graph that you see here is actually accumulation of all this power. Everything underneath this graph is accumulated here. So you can tell if you have, for example, and by the way, this graph is related to this percentage of the total energy. So if you have, for example, if we design a solar system and we use glass, and this glass, let's say, for example, has a certain transparency to certain wavelengths. Let's say it's transmit 90% of the sun energy at wavelength below 1 micrometer. So up until here, you will pass probably about 62.5% of the sun's energy into your receiver. So this is something you need to consider. You're not getting all the power that you can get. You just need to consider in your design the wavelength of your transparency of your collector. However, this is not only the only problem that we have. For example, this is the number that I quoted earlier, the solar constant, is at the atmosphere, the beginning of the atmosphere. Once you enter the Earth's atmosphere, scattering events or absorption of the light due to water molecules or scattering due to the ozone particles here in the high atmosphere decreases this radiation. And eventually what you get on a clear day, you get about 1,000 watt per meter square. Obviously this number reduces when you have clouds or just a rainy day. And the spectrum also deviates, as you can see here. The red one is what you see, the radiation at the sea level. You have absorption due to water molecules in the air at the IR, and you have here the scattering. You have reduction of the at low wavelengths. And this is actually what you see here. This reduction. This is cutting off of the blue portion of the radiation, and this is why we see in the morning when the sun is further away from us, we see the sun more red. This is because it passes through a longer path through the atmosphere, and you get reduction of this blue portion much more. And this is why we see in the evening or in the morning the sun is red, is more red than it is in the afternoon. Okay, so here is an example of the global or the total radiance on a horizontal surface for a mostly clear day, as you can see here, and a mostly cloudy day in green belt MD. And in the morning, you start with low radiation, and then it's beginning to reach the highest point. As I told you, it's about 1,000 watt per meter square at noon time, and then it's decreased again. As I told you before, the radiation of the sun is not constant. If you have a cloud or something else, you will see drops in the power generation. In a cloudy day, you see much more randomly varying sun radiation throughout the day. Now let's talk about concentrated solar power. Concentrated solar power, as I told you, there are several, three main categories. So let's start with this one. This one is the solar thermal, when you have pipes filled with water that are heated by the sun, and this hot water are transferred to a tank inside the house or outside the house, and are used to heat the water or for cooking or anything else. In Israel, this is one of the very most common technique of use of solar energy, because every house has it in Israel. It's not as common as it is in the US. And here you can see solar panels. Solar panel can be used in rural places just to generate enough electricity to run a coal box in a rural place. Or they can be used in houses to generate electricity for the houses. Or, and I don't show it here, just to generate enough electricity for a large area. And they want to make it like a plant, a solar PV-based plant. Down here are the three most common techniques to generate electricity through concentrated solar power. So what we have here, the first one to the left is the most common and widely used technique, which is a trough, parabolic trough mirror that's concentrate the light beams from the sun towards its center. In its center, in its focal point, there is a pipe filled with high thermal fluid. That fluid, later we'll see, is used to generate steam and electricity. The other technique is the tower technique, which you have a central receiver, and at this point, all the heliostat, all the mirrors throughout the field are concentrated the light radiation to the receiver, and we will talk more about it later. The third approach is to have parabolic dishes. This dish is used to concentrate all the power, not to a line, but to a focal point, where usually a Stirling engine is used to generate electricity directly from the heat of the sun. What are why do we need to use solar thermal? Or why solar thermal is so good, or we think these are the main horsepower in the future for renewable energy. So first, let's see what is the output of solar PV and wind. As you can see here, mostly in solar PV you have most of the production is during the day. However, its production can vary throughout the day, and you cannot rely on it when you need to produce power very steadily from a power plant. You don't want your power plant to say, oh, now there is a cloud in the sun, I cannot provide you electricity. And in wind, the problem is opposite. You have production during the night, mostly during the night, and not necessarily during the day. And unfortunately, the peak demand periods are between 4 p.m. to about 8 p.m., depending on the duration of the day. So in this gap, you cannot fill with solar PV or with wind. Most of all, these two techniques are direct generation. Remember, I told you that this technique directly generates electricity from the sun. So there is no known or commercially available large-scale storage for these techniques.